In this lecture, you'll learn how to perform a Laplace transform. The Laplace transform method is a good way to solve linear time-invariant differential equations which show up in dynamic systems. Specifically, we'll be taking the Laplace transform of an exponential, step, ramp, pulse, and impulse functions. On your own time, you'll need to learn how to take the Laplace transform of sines and cosines and exponentials times other functions. Also in this lecture, you'll learn how to use the initial and final value theorem, which are also helpful for analyzing dynamic systems. So let's take a look at the definition of a Laplace transform. First, we're going to be performing the Laplace transform on functions in time. And this function, f of t, is going to be 0 for any time less than 0. S is a complex variable. L is an operator, just like any operator, plus, minus, divide. It's an operator that's telling you to do something, and in this case, it's telling you to take the integral from 0 to infinity and multiply your function by e to the minus st dt. This large f of s is the symbol for the Laplace transform of f of t, and that s that's in the parentheses means that you're now working in the s domain. You've converted your function from the time domain to the s domain. So what it looks like to take the Laplace transform, you have this operator L that's operating on a function f of t, which gives you f of s, which is a complex function in the s domain. And you do this by integrating from 0 to infinity of e to the minus st times your function dt. Okay, so let's look at how to take the Laplace transform of an exponential function. So we're going to define this function as being 0 for any time less than 0, but equal to a times the exponential of minus alpha t when time is greater than or equal to 0. So both a and alpha are constants in this case. And let's take a look at what that function looks like. So if we were to plot a e to the minus alpha t, it would look something like this, where it would be an exponentially decreasing function that's approaching 0. It starts at a. Now let's take the Laplace transform. So to take the Laplace transform, we'll integrate from 0 to infinity of e to the minus st times the constant a times e to the minus alpha t dt. So first we can pull the constant a out in front of the integral, and let's combine the two exponential terms. Next we perform the integral. So now let's evaluate this term. So we have a times minus 1 divided by s plus alpha, and now we can evaluate these exponential terms. So we have e to the minus s plus alpha times infinity minus e to the minus s plus alpha times 0. So e to the minus infinity, that term goes to 0. E to the minus 0, that term is really 1. So what we're left with, and now we have to remember we have a minus sign in this numerator, and we have a minus sign in front of this exponential. So our final Laplace transform of an exponential is a divided by s plus alpha. So if you look at a Laplace transform table, you'll see this answer. The Laplace transform of an exponential function will be a divided by s plus alpha, which converts our function from the time domain to the s domain. Okay, now let's take a look at the step function. So for the step function, we'll have a function of t that equals 0 when time is less than 0, and it'll equal a constant a when time is greater than or equal to 0. So this function looks something like this. Here, let's change colors. It'll probably make it a little bit easier. So here's our function. Now let's perform the Laplace transform. So we have a divided by s, and there's a minus sign, times e to the minus s times t, and we're going to evaluate from 0 to infinity. So this becomes minus a divided by s times the quantity e to the minus s times infinity minus e to the minus s times 0. So this first term is 0, this second term is 1. So now we have a divided by s. So the Laplace transform of a constant a is a divided by s. Again, this is what you'll see if you look this up in a Laplace transform table. Okay, let's keep moving. So here's a ramp function. For f of t, when time is less than 0, that f of t will equal 0. When time is greater than or equal to 0, it's going to equal a times t. So this is a line with a slope of a and an intercept of 0. So let's take the Laplace transform of this function. So we have the Laplace transform of a of t. That equals the integral from 0 to infinity of e to the minus st a t dt. So let's pull our constant a out in front, and now we have t e to the minus st dt that we're integrating from 0 to infinity. You may remember from calculus that this is an integral that you do by parts. So to remind you of how you perform an integral by parts, we're going to integrate from a to b of some function u dv, and that'll equal u times v evaluated between a and b minus the integral from a to b of v du. So now we have to figure out what u and v are. In this case, u will equal t, and dv will equal whatever's left over, which is e to the minus st dt. So du now becomes dt, and v will be e to the minus st over s with a minus sign. So now let's perform this integral. So the integral from 0 to infinity of t times e to the minus st dt equals u times v. So u was t, and v is e to the minus st divided by a minus s. And now this is minus the integral from 0 to infinity of v times du. So v is e to the minus st divided by a minus s, and du is dt. Well, I forgot this first term is evaluated from 0 to infinity. So now for this first term we have an infinity times e to the minus infinity divided by s, a minus s, minus 0 times e to the minus 0 divided by a minus s. And then for our other term over here, we have e to the minus st divided by s squared. We're going to evaluate that between 0 and infinity. So let's go back to this first term. Although we have an infinity term here, we have an e to the minus infinity term here, which goes to 0, and that goes to 0 faster, so that first term is 0. And now we have an e to the minus 0, which is 1, but it's multiplied by 0, so this term is also 0. So we're just left with this last term. So let's evaluate that term. Okay, so let's evaluate this term. We have a minus e to the minus infinity divided by s squared minus e to the minus 0 over s squared, and this becomes 1 over s squared. Now we need to bring this back together with what we had before, and remember our original function was a times t. So we had a constant a, which was our slope. So our final answer is a divided by s squared. Or we have the Laplace transform of t is 1 divided by s squared. Alright, let's keep going. Let's look at the pulse function. So in this case, we have a function f of t that equals a divided by t sub 0. It can probably best be described in this graphical form. So let's take a look at the function. For time less than 0, our function is 0. At time 0, the function steps up to a and stays at a until some time t sub 0. At that time, the function drops back down to 0 and continues on to 0 to infinity. So in this case, we'll be taking the Laplace transform of this pulse function. Now, to understand how to perform this Laplace transform, we're going to have to take a step back and understand how to take the Laplace transform of a translated function. So let's take a look at this. Now, we've taken the Laplace transform of a step function. I'm going to use 1 as a function of t to symbolize a unit step function. So if I multiply the unit step function by some other function, f of t, and f of t can be any other function. So let's do an example here. So we're going to have a situation where our function is 0 for times less than 0, and then it's going to do a unit step, so it's going to step up to 1. And at this point, it can be any function. Now, let's say we want to translate that function in time. So if we're going to translate this function in time, essentially we just take that same function and we're going to shift it over by some time alpha. And at alpha, it's going to make a unit step and then the same function. Although that doesn't look exactly like the same function. That's supposed to represent the same function. Essentially, we've just taken what's over here on the left-hand side and we've shifted it by some time alpha. Okay, so now let's take the Laplace transform of that translated function. So we have a Laplace transform of f from t to minus alpha, and the unit step function t to minus alpha. So what this means is we have some function, any function, and we're just multiplying it by 1. And this function turns on or starts at some time alpha. It has the unit step function that turns on at that same time alpha. So now, if we look at the Laplace transform, we're going from 0 to infinity of f of t minus alpha 1 of t minus alpha. Remember, this 1 just represents a unit step, so it's really just a function for the unit step, times e to the minus st dt. Now we're going to make a substitution. So we are going to substitute tau in for t minus alpha. It's going to make our life easier. Generally, when you do a substitution with math, you're doing it because it's going to allow you to work through the mathematical steps in an easier way. So once we make that substitution, our integral now becomes f of tau times 1 of tau times e to the minus s times tau plus alpha d tau. So remember, alpha is a constant. So when we take the derivative of tau, that equals dt minus d alpha, but d alpha is 0 because alpha doesn't change. Okay, moving on. Now we have the integral from 0 to infinity, f of tau, 1 of tau. Now let's separate this term into its constant and non-constant parts. So we can have a e to the minus s tau times an e to the minus s alpha d tau. And this term is a constant. So we can pull that out in front. So now we have e to the minus s alpha times the integral from 0 to infinity of f of tau. Since 1 of t just equals 1, essentially we're just multiplying by 1 during the range that we're going to be integrating. We can remove that term. And then we're left with e to the minus s tau d tau, which equals e to the minus alpha s f of s, because this integral is just the definition of a Laplace transform. So what this ultimately means is if you take the Laplace transform of a function that's shifted in time, that equals e to the minus alpha s f of s. So it's really just the Laplace transform of the unshifted function times this term where alpha is the amount of time shift. So we'll be able to use that in the future. So now let's return back to the pulse function. So remember, the pulse function is a function that is 0 when t is less than 0, and then steps up to some value. In this case, it will step up to a value of a, and it will do that at a place of alpha, where alpha is equal to t0. So now let's return to the pulse function. Here we have a function f of t, which is equal to some constant a divided by t0, and t0 is where the pulse turns off. And so this function exists when t is greater than 0 but less than t0. Then the function returns to 0 at times greater than t0. And both a and t0 are constants in this case. So here we can take a look at what the function looks like. It starts out at 0, it bumps up to a value of a divided by t0, and then it returns to 0 at a time of t0 and then continues on at 0. So how we're going to approach solving this pulse function is we will use what we learned from the shifted time function, and we're going to build a set of functions that when they're added together will ultimately look like this pulse function. So let's do that. So f of t in this case will equal a divided by t0 times the unit function or unit step function minus a divided by t0 times the unit step function of t minus t sub 0. So what this is saying is that the function will turn on at time 0, and it will go to a value of a divided by t sub 0. And then at some time t sub 0, this function will become negative and will be subtracting that amount of a divided by t sub 0, which will ultimately remove the function and return it back to 0 at any time greater than t sub 0. So we can look at this in two parts. Really what's happening is we have a first part where we're turning on the step function, and that step function will go up to a value of a divided by t sub 0. And then we have this second function, which is a negative a divided by t sub 0 that turns on at a time of t sub 0. And when you put these two together, we get the pulse function. By rearranging some terms, we see that the Laplace transform of our function f of t, which is a pulse function, becomes a divided by t sub 0 s times the quantity of 1 minus e to the minus t sub 0 s. So that's our Laplace transform of a pulse function. Now let's do our last one. This is an impulse function. So an impulse function is like a pulse function, except for that pulse happens in an infinitesimally small amount of time. So let's draw a graph to represent what the impulse function looks like. Now there's no real way to draw this, but this is more of a representation. So in this case, what we have is a function equaling 0, and then at time 0, generally it's drawn as a little arrow. So for an impulse function, the area under this impulse curve is equal to a. So now let's take the Laplace transform. So this one's a little bit different than the ones in the past, but the Laplace transform of our function f of t, which is the limit as t0 approaches 0, so as that pulse becomes smaller to the point where the pulse duration is 0, of a divided by t0 times s times a quantity of 1 minus e to the minus s t sub 0. So this, remember that this part was the result from the Laplace transform of our pulse function. Okay, so really, if we just take the limit of our pulse function to the point where that pulse happens over an infinitesimally small amount of time, then we'll have the Laplace transform of an impulse. Now we can evaluate this limit as t sub 0 approaches 0 by taking the derivative of the numerator and denominator. So we can do d by d sub t0 of a times the quantity of 1 minus e to the minus s t0, and the derivative with respect to t sub 0 of the quantity of t0 times s, which was in the denominator, and this becomes a times s divided by s, or just a. So what this means is the Laplace transform of an impulse function is the area under that impulse, or in this case, a. Now let's take a little bit closer look at this ratio of these derivative terms where we're finding the limit. So what happened there? So when you take the derivative of this term, so let's break this out a little bit further. You take the derivative of the numerator. The first part is just a constant, so the derivative of that constant is 0, but the next part is a times s e to the minus s t sub 0, and we had two negative signs, so that part becomes positive, and then the derivative of the denominator will be s. Now we're evaluating this where t sub 0 goes to 0. So in that case, this exponential term is 1. And that's how we're left with a times s divided by s. So our final topic here is going to be looking at the initial and final value theorems. Now before we jump into the initial and final value theorems, I want to tell you about one other thing that we're going to use here. I'm going to use quite a bit in this dynamic systems course, and that is the Laplace transform of the derivative of a function f of x. So if we're going to take the Laplace transform of the derivative of a function, that equals s times the Laplace transform of the function f of t minus whatever the initial value of that function is. So for example, if we were to have dx by dt, which might represent a velocity, or we could call that x dot, the derivative of x dot is s x of s minus the initial x position. And for a second derivative, the Laplace transform is s squared times f of s minus s times the initial value, f at some time t0, minus the initial first derivative. So again, if we go back to position, and we have the second derivative of x, that is the acceleration, then if we were to take the Laplace transform, it would become s squared x of s minus s times the initial x position minus the initial velocity. Okay, so let's jump back into the initial and final value theorems. So for the initial value theorem, which really this is just the value of the system at some initial time, so that would be t0. So what this initial value theorem will allow us to do is, by looking at the Laplace transform of our function, we'll be able to find out what the initial value of that function is. And this isn't at some time where t exactly equals 0, but this is at a time just after t equals 0. So, you know, with most of the functions that we've looked at, we had them turn on at some time t equals 0. So we're saying, what is that value just to the slightly after t equals 0? And so to find out what this initial value is, what we do is we take the Laplace transform of our function and we multiply it by s. And then we take the limit as s goes to infinity. And whatever the value is when s goes to infinity, that is our initial value. Now, for the final value, you can think about this in time space. That would be the limit where t goes to infinity of our function f of t. But if you're already in the s domain and you want to find the final value or the steady state value of your system, so what happens when you let the system go on for a long time, where does it settle down to, what kind of response does it settle down to, we can take the limit as s goes to 0 of s times f of s. And so these are our initial and final values of our system when you're working in S space. So to conclude, I want to remind you what we went through in this lecture. It was focused on the Laplace transform method, and I wanted to give you the background so that you could perform Laplace transforms by hand. We did a Laplace transform of an exponential, of a step function, of a ramp function, and of both the pulse and impulse functions. Also, I showed you a way to find the initial and final values of your system when you're working in the S domain, or after you've taken the Laplace transform and you have your functions in this as when you have your functions in this S domain, you can find out what the initial and final values of the functions are. And those initial and final values will be the same initial and final values you have in time space. So it just essentially saves you a step of having to convert back to your time domain space, or if you're already working in your S domain space, it allows you just to continue working in that S domain.